Kassel in Germany from the group of Professor Ricoeur. And today my talk will be about the prospects of configuration forces in 3D finite element crack growth analysis. So as you may know, in practical cases, cracks do often have a three-dimensional character, meaning that spatial stress states can lead to very complex shapes of crack growth in terms of this results in curved crack fronts, even for pure tensile loading, and when we have mixed mode loading present, additionally crack deflection and twisting of the crack front can occur. This means that modeling of the three-dimensional crack growth is quite a challenging topic, although there is a wide range of methods that exist to quantify crack front loading and crack deflection to model crack growth. And the method that I'm concerned with is configuration forces in material space and the application in finite element analysis. So classically, the configuration forces in the finite element framework are calculated from weak formulation of the local configuration force balance. We have a conservation law multiplied with a test function integrated over a volume, what results in an equation that enables us to calculate nodal configuration forces in a finite element mesh that, for example, are an indicator for mesh quality, and they can also be used to drive adaptive meshing. When it comes to cracks, it is often assumed that the configurational force at the crack tip node of the finite element mesh is equal to minus the J integral as we know it as the path independent integral, but this is not unrestrictedly valid, as you will see later on, and this is what this work is concerned with. So to show you what the problem is, we'll have a look at this mechanical boundary value problem with some defects in it, which are indicated with this defect displacement function, virtual defect displacement function delta z. We write down the energy balance due to a movement of the defects, and then can obtain a weak form of the potential variation due to a defect displacement, where the derivative that we see here in the energy momentum tensor is transferred to our virtual defect displacement function, being this function acts as in this formulation as a test function, kind of test function. And what we can do with this formulation is we can perform straightforward discretization in terms of finite element method to use this in finite element frameworks. So we perform interpolation of our test function. This is nothing special, and we obtain a discretized form of our potential variation, where we see that there are two contributions to the force that drives the defect displacement. And the first one that we see here indicated in green is a volume-related contribution. This is kind of the classic configuration force that is often used in finite element frameworks. But what we do also see is that there is a term arising that relates to some surface contributions, meaning that this part is relevant when an element surface is part of an outer boundary, of an outer boundary of our problem. And this also means that this part will not vanish, or not necessarily vanish, at crack faces. So we have to take this into account in some special cases. And this is kind of a problem because the idea with the configuration of forces in finite element analysis is kind of attractive because of the easiness of the method. So it's very easy to use when we only have this contribution. This is standard finite element, standard finite element procedures. It is simple integration over volumes. We only use integration points. We have our shape function and our mechanical fields. This is very nice, but this part is not very nice. This is quite hard to evaluate because when we want to calculate driving force for crack tip or point on crack front, the mechanical fields involved in this part are very, very poorly represented in finite element method. So we do not want to calculate this thing, but we want to evaluate accurate driving forces, so we have to circumvent the calculation of this. And to circumvent that, we did first have a look at how the configuration of force in a three-dimensional case is related to the J integral, to the vectorial J integral. And we can see that the first component of J is only proportional to the configurational force that is, that's kind of the nice one, the volume contribution, indicated in green, but the value of J2, so the second component of J, is related to both contributions. So we have the volume contribution and the crack face contribution, and we do not want to calculate. But we do want to calculate the value for J2 because this contributes to an accurate loading analysis. So what we simply did is we took the knowledge that we have about the fields that are involved in the calculation of J2 and did a kind of analytical extension for J2 in the case of linear elastic fracture mechanics. So we put in our knowledge about fields, do some maths, calculate some integrals, and this results in an extrapolation formulation for the value of J2 that we can now calculate only from knowledge of the geometry and from those volume contribution configurational forces, so the forces that we want to calculate and only we want to calculate them. So this is a quite nice thing because we do now not need to numerically calculate the integrals at the crack phase because it is kind of hard. And we then tested this model at first for two-dimensional specialization because we have closed form solutions for that and we can compare to analytical solution. We did first do some theoretical analysis just to see how this method in theory performs when we do our extrapolation for the J integral, and then perform some finite element analysis. This is the calculation of J1 for this problem under mixed mode loading, and we can see that depending on that we had very nice convergence in analytical value with like errors of around 1%, whereas the initial error compared to the analytical solution was 7%. This is not really much, but the value improves. But this is not really new. This is relatively long known. But interesting is that one. This is the calculation of J2 for this problem under mixed mode loading without calculating crack face integrals. And we see that depending on our parameters, these are R1 and R2, these are portions of the crack face that we take into account when calculating our forces. The results are not very sensitive to the choice of these parameters, and it is not really difficult to compute quite good results with this method without calculating, without doing any complex calculations. And just to show what this has for an impact, the initial error of J2 without any improvement was 30%, and it was not a conservative one, so it's 30% less than the analytical value, while from the extrapolation it is easy to get errors that are less than 5% compared to the analytical solution. So this is quite nice. But we did all this to perform three-dimensional analysis, so I will also show a three-dimensional example. This is an inclined penny-shaped crack under uniaxial tension. This model leads to, or this load leads to a continuously changing loading along a three-dimensional crack front. And what we did is we performed our extrapolation scheme, produced some numerical results, and compared to analytical results. And what we can see here is that our numerical results do really, really good agree with the analytical results, even in this quite complex three-dimensional model, and without doing some extra calculations. So this brings me to my summary. We presented an alternative derivation of the weak formulation for the calculation of configurational forces, where the wave function is kind of a defect displacement in our weak form, and this leads to a direct interpretation of configurational forces with as vectorial J integral. Furthermore, we provided measures to improve the accuracy of the calculations, without calculating any crack phase integrals in the case of linear elastic fracture mechanics. And what is kind of interesting to mention is that these measures to prove the accuracy are not restricted to the concept of configurational forces. You can also use this with equivalent domain integrals or with classic contour integrals if you do not want to calculate some crack phase integrals. And yeah, what we will do in the future is we will employ some other visualization techniques that are that allow us for a very flexible mesh design to stress that method and test it in three-dimensional crack growth simulations and to compare what the impact of this is in the simulations. So yeah, this brings me to the end of my talk. Thank you very much for your attention, and I will be happy to answer.
Thank you very much. The paper is open for discussion or questions. Yes?
Thank you very much for your nice talk. My question is, you mentioned that the J integral will lose its path independence in the case that you have loading on the crack planes.
Right, if you do not take into account this crack phase integral term. Yes, yes.
And even if you do now your extension, how do you define the domain over which you integrate? So, or others say that what do you define as a J integral if it's path dependent?
So because we do define what we call two domains that are. This is what I showed in this. Okay, that was gone. I showed this earlier.
Censorship.
So the thing with the domains is they can be quite big, but okay, worse. But if the domains get too extensive, so the two domains that we need for the extrapolation scheme, if one of these domains get really too extensive, and I'm talking about like 10-20% of the track phase that is included in the domain, then the method will probably fail. So this is what you can see here. This is combinations of size of the first domain over size of the second domain, and we see that at this specific example, even if first domain is kind of like 10 or 20%, it is possible to get values that are kind of accurate with errors less than 5%. We think this is fine for us.
Okay. Any short question? No? So if there is no more question, let's thank again our speaker. We move now to the third presentation. Extended backface strain compliant solution for physically short crack regime in SENB 4P specimen. And it's a contribution by Hassan Saeed. I hope I pronounced it more or less correctly. And Sumsubro Chaudhuri and Wim de Waal.
Thank you.
So, up to you.